Welcome to our exploration of axiomatic systems, a fundamental concept in mathematics and philosophy. So, what exactly is an axiomatic system? An axiomatic system is a set of statements called axioms that serve as the foundation for a particular branch of mathematics or philosophy. These axioms are considered self-evident truths and are used as a basis for deriving other statements or theorems. One of the most famous examples of an axiomatic system comes from Euclid, often known as the father of geometry. Born around 325 BCE, Euclid formulated 5 axioms, or postulates, that together form the foundation of Euclidean geometry. His book, The Elements, became one of the most influential works in the history of mathematics. Let's take a closer look at each of these postulates. Number 1. To draw a straight line from any point to any other. Number 2. To produce a finite straight line continuous in a straight line. Number 3. To describe a circle with any center and radius. Number 4. That all right angles are equal to each other. Number 5. That if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two lines, if extended indefinitely, meet on that side on which are the angles less than two right angles. These postulates form the cornerstone of Euclidean geometry. They provide a foundation upon which mathematicians and scientists have built for centuries, leading to groundbreaking discoveries in mathematics and beyond. The fifth postulate, also known as a parallel postulate, is particularly interesting because it's the only one that cannot be proven using the other four. This postulate has been the subject of much debate and controversy over the centuries. Proclus, a renowned mathematician and commentator, noted attempts to prove the parallel postulate using the other four postulates, including his own and Ptolemy's, but all such proofs were flawed. Proclus also introduced an equivalent statement known as the Proclus postulate, which involves supplementary angles formed by a transversal intersecting two parallel lines. Later, in 1795, John Playfair offered an alternative known as Playfair's axiom, which simplifies the fifth postulate to state that given a line and a point not on the line, only one parallel line can be drawn through the point. Despite numerous attempts to prove the fifth postulate from other four, such as Wallis in 1663, all efforts failed, revealing the unique nature of the parallel postulate. The Sacchare quadrilateral was another significant development in exploring the nature of parallel lines. Giovanni Sacchare and later Lambert used this shape to investigate the fifth postulate. They showed that assuming angles greater or less than 90 degrees led to contradictions, sparking the idea that the fifth postulate might not be universally true. Mathematicians like Gauss, Boole, and Lobachevsky went further, developing new geometries where the fifth postulate does not hold, thus giving birth to non-Euclidean geometry. This new geometry showed that our understanding of space could go beyond the Euclidean model. Mathematicians like Gauss, Boole, and Lobachevsky went further, developing new geometries where the fifth postulate does not hold, thus giving birth to non-Euclidean geometry. This new geometry showed that our understanding of space could go beyond the Euclidean model. The exploration of these new geometries had profound implications for science and philosophy. It paved the way for modern theories, including Einstein's theory of relativity, which fundamentally changed our understanding of space and time. In conclusion, the study of axiomatic systems, starting from Euclidean geometry to the development of non-Euclidean geometries, has revolutionized our understanding of mathematics, space, and the universe itself.